you'll see that the introduction that Bozeman did for you yesterday is going to be some of the stuff that we cover today, because we are starting chemical bonding. Chemical bonding. Going to do some good bonding in here today. So, a chemical bond is a mutual electrical attraction between the nuclei and valence electrons of different atoms that bind the atoms together. Most atoms are less stable by themselves than they are when they are combined. You're going to see, folks, when we're discussing this, that it's all about stability. All about stability, and how do these elements, how do these atoms achieve stability? They fill their outer shells. Okay, they fill their outer shells. And we can do so by a few different ways. Okay, we'll do so by a few different ways. So, what these atoms want? They want stability. They want stability in their life, and they do so by filling the shells. Yesterday we saw that we have two types of chemical bonding: ionic bonding and covalent bonding. You should probably be able to tell me a little bit about ionic and covalent bonding just by based on what you saw. Anybody want to chirp up here? Anybody know something about ionic bonding? You remember it from the video yesterday? Wrote it down, forgot it?
Isn't it where that electrons like go back and forth instead of they stay in one place?
Okay, they go back and forth. How about transferred is a good word. Okay, transferred. Electrons are transferred. All right. You're going to see that when we deal with ionic bonding, we're going to talk about something called ions. Huh. Crazy. Crazy stuff there. What about covalent bonding? Sharing. Okay, so ionic bonding is the transfer of electrons. The covalent bonding is the sharing of electrons. Now, you're going to get some hints on what kind of elements like to covalently bond, what kind of elements like to ionically bond. Okay, so let's start by looking at ionic bonding. Ionic bonding. Chemical bonding that results from an electrical attraction between large numbers of cations and anions is the definition for ionic bonding. We talked about cations. We talked about anions already. What is a cation? Okay, go back a little bit in your memory. Go back into that vault. Review back into your notes. Look back. You should be able to tell me what a cation is. Who can tell me? Advia? A plussy cat. Meaning what? What's that mean? That's good. That's how I told you to remember. What's it mean, though? It has a positive charge. So has it gained or lost electrons? Lost electrons to be more plus. Okay? Remember that this is kind of confusing, gaining and losing, because we're talking about gaining and losing minuses. Okay, what was an anion? What was an anion? Who do we think of? Little Annie. Okay, little Annie ion. And little Annie ion, what does that mean? An anion. Remember? She's what? She's negative. Little Annie ion is a negative little girl. So if I have an anion that is negative, am I gaining or losing electrons? Gaining electrons. I gain electrons to become more minus. Confusion. All right. So cations and anions, positive ions, negative ions. Main group elements. Let's talk a little bit about that. Terminology, we've discussed it. What are main group elements? This is a little tougher one. Main group elements. Anyone? Anyone? It's a combination, okay? Combination of two types of elements, two blocks, okay? You need to write this down if you can't remember, because we'll use this a lot. Main group elements are the ones that are in the S and the P block. S and the P block. So when we're talking about main group elements, we're talking about groups 1 and 2, the alkali and alkaline earth metals, and then groups 13, 14, 15, 16, 17, 18, the P block. Go ahead and take out your periodic tables. We're going to be using them. Might as well get them out now. So main group elements are the S and the P blocks. Now, it says up there, main group metals. Main group metals tend to lose electrons to form positive ions. Main group nonmetals tend to gain electrons to form negative ions. So typically, okay, what you're going to see is metals are losing electrons, nonmetals are gaining electrons, if we're talking about ionic bonding, the formation of ions. Metals losing electrons positive, nonmetals gaining electrons negative. Covalent bonding. Covalent bonding is the sharing of electron pairs. The sharing of electrons. Two elements come together. They say, hey, I'll let you use one of my electrons if you let me use one of your electrons. They come up with an arrangement. They share them, and all of a sudden, everything's hunky-dory. They're both happy by the sharing of these electrons. So, ionic or covalent? How do we know whether one is ionic, whether one is covalent? Well, we need to look at something that we call electronegativity. We never, let me check, that's not never, rarely do we have purely covalent bonding. Never do we have purely ionic bonding. Okay? But we can determine the degree of the ionic or the covalent bonding based on the electronegativities of the elements involved. We talked about electronegativities when we talked about periodic trends. Okay? Electronegativity, if you find, search back in your notes, find your help sheet. Find your help sheet. Is electronegativity one of them? Yes. What is the most electronegative element on your table? Fluorine, right? Fluorine. What is electronegativity? The ability to attract electrons. The ability to attract electrons. And fluorine has the greatest electronegativity. Okay? Fluorine is the best at attracting electrons. Now, we're going to talk about two different types of covalent bonds. Two different types of covalent bonds. The first type is a non-polar covalent bond. A non-polar covalent bond. A non-polar covalent bond is where the bonding electrons are shared equally by the bonded atoms. This results in balanced distribution of the charge. Now, those bottom two bullets, okay, these are numbers you need to remember, you need to know. And the first one, ionic character, okay? Ionic character means how ionic is this? Okay? Obviously, if it's non-polar covalent bond, it's not very ionic, is it? So anywhere from 0 to 2% ionic character. What does that mean to you? Flip your periodic table to your backside. There is a chart that looks like this. Find that chart. The percent ionic character in a single chemical bond. How does the percent ionic character relate? Well, it's compared to electronegativity differences. Okay? The difference in electronegativity. So, if you find 2% ionic character, so right here, 2 to 0. 2 to 0 corresponds to 0.3 electronegativity difference. Now, that bottom part that you just wrote down, that bottom part said that the electronegativity difference was from 0 to 3. Okay? From 0 to 3, corresponding with the 2% ionic character. Now, was that what Bozeman told you yesterday? Were those the numbers Bozeman told you yesterday? I believe Bozeman told you 0.5. Now, this number, I can go up, and if I pull out my chemical books, my chemistry textbooks up there, I'll bet you that 3 different textbooks could possibly have 3 different values. So these values aren't anything that are confirmed that, yes, it is this solid. You might see differences. Why do I like to use the 0.3 instead of the 0.5 that Mr. Anderson uses? Well, because 0.3 matches up on my periodic table that we use. So I choose to use 0.3. So when we go back a slide and look at this, 0 to 2% ionic character ranges from 0 to 0.3 difference in electronegativity. How do you find the difference in electronegativity? You just subtract the elements, the electronegativity of the elements. How do you know the electronegativity of an element? It's on the periodic table. Where is it on the periodic table? Top right. So what is the electronegativity of fluorine? 3.98. It is the highest, right? 3.98. What is the electronegativity of carbon? 2.55. Okay? 2.55. Still a pretty high value if you know that 3.98 is the highest. What's the electronegativity of our buddy lithium? 0.98, somewhat lower, right? Somewhat lower. So let me ask you this. Electronegativity is what? What's the definition? The ability to what? Attract electrons. So does lithium want to attract electrons? No. What did we say? 0.98? 0.98. No. Doesn't want to attract electrons. Okay? Doesn't want to attract electrons. But does a 3.98? Yeah. Yeah. 3.98 wants to attract electrons. So let's look at this right here. Hydrogen bonded to another hydrogen. This, ladies and gentlemen, is a molecule of hydrogen. This is as simple as it gets. We know that hydrogen has one proton, one electron. Atomic number 1 on the periodic table. So as I look, here is my two different hydrogen atoms by themselves. Remember, I told you that they say, okay, I've got one electron on my outer level, you've got one electron, okay? How many electrons does it take to fill the outer level for hydrogen? 2 of them, right? Remember, the first energy level only has 2 electrons on it. So to fill that level, I only need 2 electrons. So when I have this bond right here, these guys say, okay, let's get together and let's share our 2 electrons. So if I look just at this hydrogen, it has 2 electrons in its valence, doesn't it? If I look at this one, it has 2 electrons in its valence. That is what we call a covalent bond, the sharing of those 2 electrons. How? How then do I determine whether it's polar or nonpolar? I look at the electronegativities. What's the electronegativity of hydrogen? 2 point what? 2.20, right? What's the difference in these 2 atoms of their electronegativity? Well, I've got 2 hydrogens. They're both going to have the same electronegativity, right? So I say my difference is going to be 0. So what is my ionic character for this particular bond? 0. It's no ionic. It's not ionic. Okay, so this is a situation where I have a purely covalent bond. Okay, a purely nonpolar covalent bond. So if we look, here is a nonpolar covalent bond. Here are the 2 hydrogens. They're sharing these electrons. Anybody winning that tug of war? This hydrogen's pulling at a 2.1. This hydrogen's pulling at a 2.1. Nobody's winning. Non-polar. Our next type of a covalent bond is a polar covalent bond. A covalent bond in which the bonding atoms have unequal attraction for the shared electrons. We just showed that slide of a tug of war between 2 electrons. Well, in a polar covalent bond, one of the atoms is winning the tug of war. Somebody's winning that pull. Which one is winning that pull? The one with the greater electronegativity. Because higher electronegativity means that they want to attract electrons better. The values we assign: bonding with an ionic character between 2% and 51%. So greater than 2, less than 51 is going to be what we call polar covalent, all right? Electronegativity differences, greater than 1.3, less than 1.6. Greater than 1.3, less than 1.6. Let's look right here. We have, if it's exactly 2% ionic character, if it's 2% ionic character, then I'm going to go with the nonpolar. Okay? So if it's greater than 2, less than 51. Okay? If you're going to get that technical. Okay? Let's look at electronegativities here. Okay? What's the electronegativity of hydrogen? 2.20, right? What's the electronegativity of chlorine? 3.16. So if I do my math, 3.16, 2.20, and I subtract them, 6, 2, 1. I'm going to get 0.96. Does that seem right? Does that seem right? 6 minus 0 has always been 6 in my book, but 0.96, does that fall in my range here? Does it fall in between 0.3 and 1.6? Absolutely. So I can consider this a polar covalent bond because it falls into that range. So who's winning the tug of war for those electrons? Who's winning? Chlorine, because chlorine's pulling and it has a higher electronegativity. So chlorine, look at that. Ooh, got some teeth to him there. Chlorine is winning the tug of war for those electrons, for those 2 electrons. Now let's get into ionic. Let's get into ionic. Well, I don't want to do that. Ionic bonding. Ionic bonding has uneven distribution of charge. Bonds that have higher than a 51%, well, I guess 51 and higher, ionic character. Makes sense. They're more than half ionic, right? 51% is more than half, so they're more than half ionic. So they have an ionic character, ionic bond. The electronegativity differences range between 2.1 and 3.3. So the difference in electronegativity, 2.1, 3.3. Now, let's look at these 2 right here. Okay? What is the electronegativity? We just said electronegativity for chlorine was 3.16, right? What's the electronegativity for sodium? Okay, go ahead. We talked about the difference in electronegativity, 3.16 and 0.93. Okay, so when you subtract those 2 out, what do you get? What do you get? 2.23? Sound right? Okay. Is that falling in the range? Okay. Is that falling in the range that we gave? Yes. So we have an ionic bond. So what is really happening? If you look right here at sodium, notice that it has one valence electron. What is a valence electron? Have we defined valence electron? Electrons in the outermost energy level are valence electrons. So sodium has one valence electron. Notice behind this shell, look at this one. This second shell right there is a filled shell, isn't it? That's a filled shell. And it has one extra one. Now look at chlorine here. Look at chlorine. It has it has 7 valence electrons. What chlorine would like to do is chlorine would like to have 8 valence electrons to fill its shell. So, that's why chlorine is pulling at a 3.16. It wants to attract that one electron. Sodium wants to get rid of its electron because the shell behind that is filled. So if you look down here, what has happened is sodium said, go ahead and take that electron, and gave it to chlorine. So you count the electrons now on chlorine's valence, it's 8 on the valence level, 18 total. If you look at sodium, sodium is 8 on its valence electrons, but it gave one up, didn't it? It gave one up. So if I lose electrons, I become more what? Positive. How many did sodium lose? How many electrons did sodium lose? 1. So what I'm going to do is sodium is going to be Na plus 1 right here because it has 11 protons and only 10 electrons. Has 1 more plus than minus, right? Chlorine, 17 protons, 18 electrons. It has 1 more minus than plus, right? So chlorine is going to be Cl minus. Ladies and gentlemen, we have an anion, we have a cation. Anions, cations, those are ionic bonds. Ionic bonds. So when we're dealing with this ionic bonding, we are dealing with anions, cations, ions. And how do they become ions? By gaining and losing electrons. Now, that leads us to a point. That leads us to a point. Look at your numbers. Ionic bonding, I gave you a 2.1, right? Covalent bonding, the highest one was a 1.6. Does that make sense? What about in between? What about in between? Well, that leaves us a problem that gives us a gap. You see the rule number 4, okay? And you might say, well, what are the first 3 rules? Well, that was just the different 0 to 0.3, and then the greater than 0.3, the less than 1.6, and then the 2.1 up. Well, here's the 4th one. If it falls between, and don't be confused, what's delta En? Okay? Delta, anytime you see that triangle, that is a delta. That's a Greek delta. Triangle in science means change. So delta means change. Delta En is the change in electronegativity. So if I have an electronegativity, a difference in between 1.6 and 2.1, I have to look at what the atoms are involved. What elements am I dealing with? If I'm dealing with a metal, okay, if I have a metal as one of my two elements, we're going to call that ionic bonding. If I have only nonmetals, then we're going to refer to that as a covalent bond. So we're going to take these electronegativity differences, and if it falls in between the 1.6 and 2.1, we have to look at the elements involved. Look at the elements involved. And it's not real tough to do. You're going to see here, it's not real tough to do. Finally, the final thing I have here is just, oh, wait, I got more. My bad. Okay. Magnesium and chlorine. Give me some electronegativities. What's magnesium? We know chlorine, 3.16. What? What's magnesium? 1.31. So, do your math. 1.31 and 3.16. What's that give you? What's that give you? 1.85? Jeez, you guys, what kind of math do you guys do? 2. What? 2? Oh, okay. All right. 3.16 minus 1.31 gives me 1.85. Does that fall in between the range? Yes, it does. It's in between 1.6 and it's in between 2.1. So I look. What am I dealing with? What is magnesium? Metal, nonmetal, metalloid. Magnesium's a metal. So what would I consider this bond? Ionic, because that is a metal involved. To be polar covalent, you would have to have 2 nonmetals. I have a metal involved? Yes. Therefore, I have an ionic bond. Now, here's just a table that I got out of a book, okay, that just has a generalization of values, okay? Generalization of values. You can see that the difference in electronegativity corresponds with the ionic character, and you get values, okay? Now, this table should be in your head, okay? This table should be in your head because it's just listing values. If you know those 4 different electronegativity things, then this table is not that big of a deal to you, okay? But it just, nonetheless, it's just a table that I have that we've used for electronegativity.